Okay, let's get started. You should really listen up today because all the things I'm going to talk about are very, very, very relevant to the midterm. And so anybody who you know is not in class today, share your notes with them or something. Anyway, so I'm going to go through fairly systematically the material I think is important that we've done since the last midterm, and that's what the emphasis on the midterm on Monday is going to be on. So this first sort of topic that we covered after the last midterm was motions. So these are motions in Rn specifically. And they're these things that are bijections from Rn to Rn and which preserve lengths between any pair of points. So they're these sorts of things that sort of twist Rn around without really changing anything that you may have embedded in it, for instance. And what we saw was that if you have a motion in Rn, so we went through a certain amount of detail to actually show that this is true, and it's a sort of important point, that any motion can be written in a sort of canonical form. It can be written as the composition of a translation, which is possibly trivial, a rotation, again possibly trivial, and either some fixed reflection or the identity. And we sort of identified groups that these things belong to. So for instance, a translation looks like an element of Rn. I mean, you're just choosing where you want to translate the origin to, and that determines where every other point is translated to. The things that we called rotations were these things in the special orthogonal group, which was embedded or arose as the kernel of the determinant map in the orthogonal group On. So it's important that you remember what the definition of the orthogonal group is. It's, well, equivalently the set of matrices in GLN such that the transpose of that matrix is its own inverse, or put another way, the column vectors of the matrix form an orthonormal basis. And we sort of had this theory of bilinear forms, and we saw how that connected the characterization by transpose equals inverse and orthonormal bases. Now, this reflection or identity thing looks like an element of, well, a group like plus or minus 1. And in fact, On is the product of, well, I mean, not necessarily plus or minus the identity, but, sort of plus or minus a reflection kind of, well, I should maybe put it this way. The group generated by reflection, this thing is isomorphic to plus or minus 1. Direct product of these things, and then these things came together to form the group of all motions. So now we also saw something structural about this. For instance, we saw that the set of translations, which is this thing isomorphic to Rn, I mean, it's very easy to think of it as just being another copy of the additive group Rn, is normal subgroup of the group of all motions. Why? Well, it arises as the kernel of a natural map from the group of all motions to On. So you should be aware that there's such a map. And we then went on to look at a sort of special case. We took n equals 2, and we looked at motions in the plane. So much of what that entailed was analyzing first the finite subgroups of the group of all motions in the plane, and then looking further at the discrete subgroups of the group of all motions in the plane. And ultimately, we classified these things. So classification of discrete subgroups. So remember, discrete means that there is a sort of minimum magnitude to the angle of any rotation in the subgroup and to the magnitude of a translation in the subgroup. And part of the analysis here was via decomposing such a subgroup, any discrete subgroup, into a translation subgroup. Which was a lattice. And a subgroup of O2. We characterize which ones actually come up. So, reminder, please do pick up your graded assignments from the CA mailboxes. There were a whole lot of assignments graded this past week, and so the mailboxes are overflowing, I think. Let's see. So, I mean, just a note in preparation for the midterm, you don't have to worry too much about this. I mean, you don't have to go back and memorize every single detail about how we classified these things. The point is simply that you have some idea of what's going on. I mean, it would take well over an hour to just go through proofs of the entire classification. So you can expect that that's not going to be a question on the midterm. But I mean, you should be aware of the sort of basic structure of what's going on here. So at any rate, the subgroups of O2 which arise, and these are somehow coordinated with the possible lattices, are Cn, and I'm using the notation D2n, which is, I believe, the notation Dn for Artin, where n equals 1, 2, 3, 4, or 6. I mean, in fact, we got a lot more sort of structural information. We coordinated these things with other possible lattices, but you don't need to worry about that too much. Okay, so then what we did is we said, well, a lot of the sorts of things that we discovered when studying motions can be really abstracted, and making this sort of abstraction will be very, very useful to us because we can find all sorts of interesting sets for groups to operate on. For instance, the group itself. So we started looking at sort of notions of abstract symmetry or group actions. So we had a notion of what it means, completely axiomatized what it means for a group to act on a set. So this sort of curvy arrow thing, I just mean acts on. It's just a convenient notation. So it's an action. And you should know, of course, the definition of an action. I mean, it, in fact, really doesn't say very much. It mostly just says that we have some sort of composition G cross S to S, and the identity element acts on S, just any element of S, just sending it to itself. And we demanded a sort of associativity for composition. So if we act on S by GG prime, that should be the same as G acting on G prime acting on S. Which isn't, sort of an a priori true thing if you just have a random function from G cross S to S. And this was really, really very necessary. I mean, it's what allows you to sort of get all of the structural results about group actions. So, given some element of the set being acted on, we associated a couple of very important sets to it. One of them being another subset of the set being acted on. So, given this S and S, we have a couple of things. An orbit, which is just the set of all images, all translates of this little s under elements of the group. So this is orbit. We also associated something called stabilizer. This is stabilizer. And this is the set of all G and G such that G of S equals S. And this thing is in fact a subgroup. And these things are very, very closely related. What we showed is, in fact, that there's a sort of neat way of characterizing all group actions in terms of this language. So here's the proposition. There's a natural G-set structure on the coset space G mod GS, G mod the stabilizer of some element S. And the point is that this thing is, as a G-set, isomorphic to the orbit of S. The orbit of S is certainly a natural G-set. I mean, it, by hypothesis, satisfies the group action axioms and is closed. It's, everything's fine. It's completely closed under this action because that's how you define it. So what's this map specifically? Well, it takes the coset GGS and maps it to the image of S under G. So this thing is isomorphism of G sets. In other words, sets with G actions. And as a corollary of this, we saw, for instance, that the orders sort of match up in a nice way, assuming you have finiteness. Assuming finiteness of G and S, well, in fact, it suffices to assume finiteness of G because then the orbit is necessarily finite. We have cardinality of, the order of G, the order of GS times the order of OS, which you can also get by sort of a very basic counting argument. We also saw another important thing, and that is, this is a very useful sort of result. It's something that you can sort of apply in many cases, and that is that if you consider the stabilizer of a translate of an element, you can relate it to the stabilizer of the original element by conjugation. So this is the conjugate subgroup, conjugated by whatever you translated the element of the G set by. And you should know some basic, this isn't extremely important, but it's surely important that you review some examples of applications of these formulas. And it's certainly absolutely critical that at the very least you have an idea of that you not only have an idea, but that you be able to write down completely explicitly the definitions of anything I'm writing here. If you don't know the definition of a word here, you better learn it, because there are going to be plenty of definitions that you have to give on the exam. Yeah?
Just along those lines, can you explain a little more what you mean by G-set?
So G-set is a set equipped with a group action. So this thing is a G-set because it has an action of G on it. So set equipped with G action, G-set are synonyms. Okay. Okay. Yeah, so now let's fix a group G and a set S. So I'm not assuming that a priori I have some sort of action of G on this set S. But I want to sort of classify the actions, the possible ways that I can make this set S into a G set. In other words, the possible ways I can have an action of G on S. So the theorem is there is a one-to-one correspondence between actions of G on S, and homomorphisms, these are specifically group homomorphisms, from G to the symmetric group on S. So remember, the symmetric group on S is a set of bijections from S to S. And it forms a group. We saw that ages ago. So these things are in correspondence. So if we have, for instance, some fixed action, so I suppose we take some action of G on S, then this thing gets mapped to the homomorphism, which takes an element of G, and then we have to give some element of the symmetric group on S. And what you show is that the map S goes to GS is indeed a bijection from big S to big S. So we then have to verify this thing is a homomorphism, but that's not hard. So there's a homomorphism induced by this action from G to the symmetric group on S. Going the other way, if we have such a thing, this gets mapped to the action where G acting on S is defined by phi of G acting on S. Remember, phi of G is a homomorphism from G to the symmetric group on S, so we can then apply phi of G to an element of S, and this is how we define the action. And this thing is a nice sort of bijective correspondence. And it just looks like some abstract nonsense, but it actually has some interesting applications. You might want to think about how one applies, at the very least, observations about the relationship between the size of G and the size of S. That could be very useful. So anyway, here's just a sort of very basic remark. If the size of S is n, well, I mean, symmetric group on S is just Sn, not canonically identified. I mean, it relies on taking the elements of S and labeling them 1 through n or whatever, but that's not a big deal. So the point is, at least, that if we have some action of G on S, then we have a homomorphism from G to Sn. Now this is especially useful in cases where, for instance, G acts on itself by left translation, because it tells you that you have a very special homomorphism, one that sort of characterizes the group going from G to Sn. So what do I mean by that? Well, in particular, we can act on G itself by left translation. So if I have a group of order n, then I also have group homomorphism G to Sn, and we know more about it. It's in fact injective. And that just follows because, I call this thing phi of G under this correspondence, remember, is just this thing that's telling you what the action is. But we know that the element G is in fact determined by left translation on the group itself. In fact, it's determined by acting just on one of those elements, the identity element. So this map is injective. Now, there's another very important action of G on itself. So which one am I thinking of? Conjugation. Fabulous. Another action of G acting on itself. This one is by conjugation. In other words, G applied to some element X of the group is conjugate. And this is the source of a very useful formula, something called the class equation. So if I look at the order of G, then I know that I can break it up into the sum of the orders of the orbits for this action. I mean, that's just sort of in general true. This is the sum over all of the orbit it's in G for this action. But what do we call an orbit in G for the action by conjugation? A conjugacy class. So this is the class equation. You should certainly know this equation and be able to apply it. In particular, you should be aware of a very, very critical fact about the class equation, and that is that conjugacy classes of order 1, if I have some conjugacy class of order 1, then we know something about the element of that conjugacy class. So what do we know? It's in the center. And this has some nice immediate applications. For instance, to p groups. You should know what a p group is. For instance, we know from the class equation that a p group has center of order greater than 1. And we know other things like that every group of order p squared is abelian. So those are useful sort of facts. Then we moved on to another sort of thing from this, which is actually fairly closely related. We talked about simple groups. In other words, G such that if I have a normal subgroup, that normal subgroup is either the trivial subgroup or all of G. So a point here is that these groups are structurally important for a number of reasons. But here's an example of a reason why they might be structurally important. If I have a homomorphism from G to G prime, and I assume that G is simple, then what do I know about the homomorphism? Yes?
Its kernel will be either 0 or everything. So
exactly.
Homomorphism will be either injective, either constant 0.
Exactly. So for instance, if we have, as you say, a homomorphism from a simple group to another group, then we know that that homomorphism is injective or trivial. This is the sort of thing we leveraged in Sylow theory. So something more that we can say about normal subgroups and conjugacy. So if H is a normal subgroup of G, then H is in fact a union of conjugacy classes. And this sort of thing we found useful because it allowed us to show in some cases where we could explicitly write out the class equation that a group was not simple, for instance. So for instance, class equation plus the fact that subgroup of a group must have divisible orders. These facts together can sometimes be used to show a group is simple. We saw an example of this. This isn't really very important, but it's good that you be aware of this. Should you ever need to show that a particular group is simple or not. Okay, let's move on. So, next thing we talked about was CeeLo theory. So remember, CeeLo theorem said, this is definitely a good sort of thing to have very carefully memorized. Being able to state in your sleep the CeeLo theorems is definitely a useful thing. So if I have a group of order p to the e times m, where this factor, this power of p is not trivial. So in other words, the exponent is greater than or equal to 1. Moreover, this m is relatively prime to p. In other words, p does not divide m. So under those hypotheses, then we know a lot about the CeeLo p subgroups. I mean, in particular, you should know the definition of a CeeLo p subgroup, of course. You can't really know the theorem unless you know what a CeeLo p subgroup is. So the number of CeeLo p subgroups subgroups of order p to the e satisfies a couple of things. First of all, number of them is congruent to 1 mod p. Secondly, number of them divides m. We saw lots of great examples of how we could just use this fact. This fact alone gets you a lot of information. But a lot more can be said. For instance, every two CeeLo p subgroups are conjugate. It was also a very useful sort of fact. And then one that doesn't get taken advantage of quite so often in basic applications, but can be useful in less basic applications, is that if I have a subgroup G with order divisible by P, then there is a CeeLo p subgroup of G such that its intersection with this subgroup is CeeLo p subgroup of K. Just one remark. I mean, recall that, for instance, this is the result. I mean, we can draw from this first part things like that the number of CeeLo p subgroups must be 1, and then we can draw from this that in that case the CeeLo p subgroup is normal. So that's definitely a useful thing to remember. And so here are a couple of applications we saw. Couple of applications. So one of the first applications we saw was to groups of order PQ, where P less than Q are primes. You should definitely know this. So we know, for instance, that the number of CeLO Q subgroups is 1. We also took a brief look at groups of order 12. That seems like an awful lot to put on a midterm. Okay. Next thing we saw was conjugacy in Sn. So the underlying structural result about Sn that we sort of use repeatedly is that any permutation has a disjoint cycle decomposition. If I have some permutation on n letters, I can rewrite it as a product, say A11, A1L1, dot, 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 AK1, AKLK, where these are disjoint cycles. Of course, disjoint means that the support, the things that I list in this notation for the cycle, have trivial intersection, have empty intersection. So they're disjoint. And then from this, we get a lot of information about conjugacy. We can write down exactly what conjugation means. So conjugation by some element tau in Sn, some other permutation, has a sort of visible effect on the disjoint cycle decomposition. So if I conjugate, this thing has disjoint cycle decomposition tau of A11 dot, 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 tau of A1L1 dot, 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 tau of AK1 dot, 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 tau AKLK. Well, it's pretty obvious what I'm saying. And we moved on to ring theory. So rings. Rings are things with two interacting operations. So they have this plus operation, which is an abelian group. And we have an identity element, which is denoted 0. And then there's a multiplication operation, which is associative and has an identity of its own, 1. But notice that we don't, for instance, request that there are inverses. In fact, it would be quite silly to, in general, request inverses on all of R because it's not hard to show that 0 couldn't possibly have an inverse. And then, of course, these have to interact. So we demand some sort of distributivity property. And moreover, we generally assume, in order to get good structural results, we generally assume commutativity as well. Specifically, commutativity of the multiplication operation. Although, I mean, of course, we'll sort of explicitly say if we're assuming that or not. So what? Well, we had a notion of homomorphism and ideal that sort of came naturally out of the definition of ring. So there are homomorphisms. I won't define them for you, except to notate that they preserve the additive group structure, they preserve the multiplication, and they preserve 1. And it's necessary to make this as a separate hypothesis from this, because it's not a group under multiplication. And we saw ideals. So what are these things? Well, they're subgroups of the additive group, in other words, of the ring under the addition operation, and they're stable under multiplication by R. And these things were analogs of normal subgroups. However, on an exam, it would not be sufficient, for instance, to say, for the definition of an ideal, it's the analog for rings of a normal subgroup. You want to actually explicitly give the definition. But here are some useful facts about them. The kernel of any homomorphism is an ideal. But there's a converse to that statement, because we saw that there's a good quotient construction. And that quotient construction implies in particular that every ideal I is kernel of some homomorphism, but in fact we can explicitly write down a homomorphism which has I as a kernel, namely the natural projection map. R goes to R bar, which is R mod I, the quotient. And you should remember what a principal ideal is. This is a specific type of ideal. Not all ideals are necessarily principal, although there are rings in which every ideal is principal. Repeat that in a minute. So here's an important proposition. If I have a commutative ring, then that ring is a field if and only if what? Sorry? If and only if this ring has exactly two ideals. Exactly two ideals. Exactly two ideals. Namely, 0 and the unit ideal, 1, which is all of the ring. So I hinted at a question a second ago, namely, when are ideals always principal? For what rings are ideals always principal? When are ideals principal? And the main tool there was the Euclidean algorithm. So, Euclidean algorithm implied, for instance, that every ideal of the ring of integers is principal. Another good case, when F is a field, we found that there was a Euclidean algorithm on the ring of polynomials over F. So there's a Euclidean algorithm for f of x, a set of ring of polynomials with coefficients in f. And that implies that every ideal of f adjoint x is principal. By the same sort of argument as for the ring of integers, sort of basic Euclidean algorithm thing. Now, we've talked a good deal about quotients in class, and we also saw something important about the relationship between the set of ideals of a quotient ring and the ideals of the original ring. So, ideals of quotients. So suppose I have some ideal I, fix this thing. Fix I subset of R ideal in a commutative ring. So the structural result we found was that the ideals of the quotient of R by I correspond to the ideals J of R containing I. And this correspondence is realized by the natural homomorphism from the ring to its quotient. So if F denotes the canonical map, then given some J bar, an ideal of R bar, this thing gets mapped to its inverse image. Going the other way, if I have an ideal of R which contains I, then I just consider its direct image, f of j. And the first isomorphism theorem tells us more, tells us that this is a really, really good correspondence because R mod j is canonically isomorphic to R bar mod j bar. So this is the map induced by R going to R bar equals R mod I going to R bar mod j bar. Point being, this map is surjective with kernel J. And so by the first isomorphism theorem, there's a canonical map like this. Then we started talking about creating relations. So I'm going to talk about a much too simple example. So you should think about somewhat more complicated examples. So here's a very simple example of creating relations. So here's the proposition that if I have some field f, and I consider the ring of polynomials with coefficients in f, and I make the relation that x is equal to 0, then what do you think this ring looks like? It just looks like f again. Exactly. So the heuristic reason for this is that we've added the relation make x equal to 0. I mean, remember, that's what quotienting does. When you quotient by something, you're saying take all the things in the ideal or the normal subgroup or whatever that you're quotienting by and make them all 0. So x is made equal to 0. But you should be able to prove this. It's insufficient on an exam to say, well, heuristically, this is making x equal to 0. Therefore, it all works out. Because, as you discovered on the last homework assignment, this is actually a very subtle sort of thing. If I take f of x and I mod out by x squared minus 1, for instance, I don't get f, even though it looks like I'm just adding the relation x equals 1. It doesn't work that way always. In that case, as you saw in the homework, f of x mod x squared minus 1 is actually isomorphic to f cross f. But in this simple example, let's just look at the proof. Let's just highlight the most important steps. So there certainly is a perfectly legitimate ring homomorphism going from f adjoint x to f. Specifically, I can take a polynomial and I can map it to its evaluation at 0. That's certainly an element of f. And it is completely trivial that this thing is actually a ring homomorphism. Now, this thing is surjective. Because if I just let p of x be the constant polynomial, p of x equals c in f, then phi of p is c. So this thing is indeed surjective. The point is that this tells us by the first isomorphism theorem by the first isomorphism theorem, there is a natural isomorphism between f of x modulo the kernel of this map phi and f. So of course our goal is to show that the kernel is exactly the ideal generated by x, the principal ideal generated by x. Well, this is not too hard to see. So the kernel is the set of things which map to 0. Well, thing maps to 0 if and only if 0 is a root of p of x. But we saw over fields that a polynomial has a particular root if and only if x minus that root actually divides the polynomial. So this is true if and only if p of x equals x times q of x, where q is some other polynomial. This is some other polynomial in f of x. Why is this? What's a way of showing the fact I just stated that root implies a divisibility like this? Yeah. Exactly. It follows immediately from the Euclidean algorithm because I know that I can write p equals xq plus some remainder. But by evaluating all these things at 0, I get that the remainder must be 0 at 0. But the remainder, by the Euclidean algorithm, has degree less than this, less than the degree of what you're dividing by. So it must be constant. So if a constant evaluated at 0 is 0, then it must be 0. But this generalizes. This works if I have any root. So, I know that if p of c equals 0, then p of x as a polynomial equals x minus c times q of x. This is a general fact. But this statement is exactly the statement that p of x is in the principal ideal generated by x. So indeed, the kernel is exactly equal to the principal ideal generated by x. That's a good place to stop. Good luck.